Hi class, today we're going to be talking about section 2.7, transformations of functions. And so really we're going to lean a lot on our previous video on library of functions, where we had kind of our base functions, our absolute value function, our square root function, our cube root function, our square function, our reciprocal function, our cube function, and so on and so on. And when it comes down to the types of transformations that we're going to talk about, there are really just a few. H, S, R, and V. And this is the way that I remember them all and kind of the way that we do them. But we have what is called a horizontal shift. We have our stretch or shrink. We have our reflections. And we have our vertical shifts. And so I introduced them in this order because this is the order that we applied them. H, S, R, and V. So you might remember the mnemonic: help students remember variables. Because H, S, R, and V is the sequence we'll apply them in, but I'm going to introduce them one at a time. So the first ones we're going to talk about actually are going to be both our vertical and horizontal shifts. And so consider a base function f of x equals the absolute value of x. And so let me go ahead and draw a coordinate grid. Right, we have our x and our y. And we'll go ahead and make a table, x, y. And we'll go from -3 all the way up to 3. And so the absolute value of -3 is 3. The absolute value of -2 is 2. The absolute value of -1 is 1. The absolute value of 0 is 0. And the absolute value of positive numbers are just those numbers. And so if I were to then plot those points, right, and we remember this from last time, we have a graph that looks something, if I could hit those points a little bit better maybe, like that, right? And so that's a really poorly drawn absolute value graph. Now what would happen if instead of looking at f of x equals the absolute value of x, instead we looked at g of x equals the absolute value of x plus 2. So this column here is f of x, and actually now I'm going to rewrite that down below. If we have g of x is the absolute value of x plus 2, I'm just going to go ahead and add another column for g of x. So g of -3 is our absolute value of x, but then we add 2. So the absolute value of -3 is 3. We add 2 to get 5. The absolute value of -2 is 2. Add 2 to get 4. Absolute value of -1 is 1. Add 2 to get 3. The absolute value of 0 is 0. Add 2 to get 2, 3, 4, and 5. And so let me pick a different color. I'll use green. We plot those points. So at 0, we're at 1, 2, and we're up, up, and up 1. And now if we draw that this way, Ooh, struggle. That's our g of x. And so let me go back and write. This is our f of x. And if you want to visually see that increase, from this point up to that point, as is the case with all of them, is a distance of 2. Right? And so we can see when we add this 2 on the outside, we essentially move all of our points up 2 on the graph. And then to see one more similar example, use light blue for this, call h of x the absolute value of x minus 3 now. So I have another column, h of x, and we're just going to go ahead and subtract 3 from our y values for f of x. So here we have 0, -1, -2, -3, and then, oh, I'm good. 1 minus 3 is -2, -1, and 0. And so again, plotting those, 1, 2, 3, -2, -1, 0, -2, -1, 0. And here we have h of x. So generally speaking, whenever we have some function plus a constant or some function minus a constant, that's a vertical shift. And so if you have y equals x, right, is our identity function, x plus 2 is just that graph shifted up 2 units, or minus 5, down 5 units. And so, right, as we start to understand these transformations of graphs, you'll see, oh, that's why we care about our library of functions, because once we know those basic functions, when we want to graph them, we just apply these transformations. And so let's talk about, we've talked about vertical shifts, and so now we'll consider horizontal shift. And so before, this is an aside, vertical would be an f of x plus or minus some constant, but a horizontal shift is going to be something like plus or minus d on the inside of the function. You're like, well, what does that mean? How is that different? Well, let f of x be the absolute value of x. Well, if g of x is the absolute value of x minus 2, what does that look like in our table? So x, f of x, g of x. So x, we'll just do the same, -3, -2, -1, 0, 1, 2, 3. Absolute value. Take the value of it. But now, if I'm finding g of, if x is -3, -3 minus 2 is -5, and then the absolute value of -5 is 5. And if I have -2 for my x, -2 minus 2 is -4, the absolute value is 4. -1 minus 2 is -1, nope. -1 minus 2 is -3, so absolute value is 3. 0 minus 2 is -2, absolute value is 2. 1 minus 2, absolute value of 2 is 1. I think I said that wrong. 1 minus 2 is -1, absolute value is that. 2 minus 2 is 0, absolute value is 0. 3 minus 2 is 1, absolute value is 1. I'm going to go ahead and try to include a 4 down here. Hope it won't let me work it. But we have g of 4 is 4 minus 2 is 2. Its absolute value is 2. And so now, if I graph this, and again, let's go ahead. I'll just use black for my f of x. What you see, that 3 goes here, that 2 goes here, 1 goes here, 0 goes here, 1, 2. And so what happens if we plot these points? At 0, we're at 2. At -1, we're at 3. At -2, we're at 4. At -3, we're at 5. At 1, or at, this is where it's unfortunate that my work got a little too messy, because I think, alright, at 0 we're at 2, at 1 we're at 1, at 2 we're at 0, at 3 we're at 1, and at 4 we're at 2. There we go. It was a struggle, but we got there, and that's g of x. And so these arrows I was drawing shows us how what happens is we end up shifting our graph 2 units right. And you're like, well, but when we subtract, we go left. Yes, but because we're taking a value off of our 2, we need to be at 2 to get where we were at 0 on the original function, right? Because 2 minus 2 is 0. And so let's consider one more sort of horizontal. So now we're going to have h of x equals the absolute value of x plus 1. So here we have h of x. -3 plus 1 is -2. -2 plus 1 is -1. -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. And so on and so on. And so to plot that, we have our 0 here. 1, 2, 3. 0, 1, 2. This is our h of x, which is this base graph shifted 1 unit to the left. And so when we add, we have a left. And when we subtract, we have a right. And I would say, if you're not sure, or you can't remember, oh, was it when we add we go right, or was it left? Just go ahead and pick your point. Usually where your x equals 0 is a decent point. Get that one in, and then maybe do one more point, say at 1. And you're like, oh, well, that goes to 1 and 2. All right, I know what this graph is going to look like then. So our shifts occur either vertically, and that's when our addition is outside of our function, or horizontally when they're inside. Let's consider reflections. Reflections. A reflection can happen one of two ways. It can happen about the x-axis or about the y-axis. And just like when we talked about our shift, we had a general form. This is when we're looking at not f of x plus 2, but if we're looking at either negative f of x or f of negative x. And so let's look at a couple examples. Let f of x be x squared. And so if you want x, f of x, -2, -1, 0, 1, 2, 4, 1, 0, 1, 4. And when we graph this, 0, 1, 3, 4, 1, 4, and f of x looks something like that. It needs to go all the way down. There we go. That's a little bit better. And so that's f of x. But now, so let g of x be negative f of x. Well, that means we're at negative 4, negative 1, 0, negative 1, negative 4. So if we plot those those new points, we have something that looks like this. That's our g of x. And so we call that a reflection about the x-axis because each of these points, which were, say, 4 units above, are now 4 units below, right? So the distance from the axis is preserved, but it reflects across. And now let's try, if that's g of x, let h of x be negative I need to give us a new graph. I'm going to go to the next slide. So here, if we're talking about, so that was reflections about the x-axis. Here we're going to talk about reflections about the y-axis. Let f of x equal x cubed. So graph this, x and f of x. Negative 2, negative 1, 0, 1, 2. Negative 2 cubed is negative 8. Negative 1, 0, 1, 8. So if I put those points, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And it looks, oh wait, nope. Now we need to go one to the left. 1, and then 1, 2, 3, 4, 5, 6, 7, 8. Right, and so we had something that looks like that. And you'll see why I chose this one instead of continuing with x squared. F of x. And now let g of x, I'll pick a new color. G of x is f of negative x. So let's find negative x first, and we'll find f of negative x. So negative x is 2, 1, 0, negative 1, negative 2. And our function value is that cube, so we have 8, 1, 0, negative 1, negative 8. But our ordered pairs, be careful, are still negative 2, 8. So negative 2, 3, 4, 5, 6, 7, 8. Negative 1, 1, negative 1, 1, 0, 0, 1, negative 1, and 2, negative 8. So that now we have something that looks like this. Right? And so what happened there was that all of our number spots swapped places. And so while before we were, say, 2 to the left, now we're 2 to the right. Or 1 to the left, 1 to the right. And so here we get a reflection across that y-axis. And so again, a good place to start, drawing your table. And as you get more comfortable, you'll be able to just proceed from your base graph. You'll be like, that's negative x. And so all I need to do is flip it around the axis. So going back here, why didn't I just stick with this example? Let me pick, I'll use purple. Negative, or nope, f of negative x. Well, if I take negative 2's opposites, 2 is 4. Negative 1's opposite is 1, squared is 1. 0, opposite 0, squared 0. 1, its opposite is negative 1, but squared is still 1. 2's opposite is negative 2, but squared is still 4. And so, because our x values didn't change, f of negative x looks exactly the same. Because this function, f of x, is already symmetric about the y-axis. So if you would flip it, it doesn't look any different. And so that's why I was like, actually, let's look at x cubed, so we can actually see the flipping process in action. All right. Next. So we've done h. So we had help students remember variables. We had our horizontal shifts. We've already done those. We've done our reflections. We've done our vertical shifts. And so now we need to talk about our stretches, or our shrinks. And these we're going to break down into two groups. We have vertical stretch / shrink. And our book, just for a note, uses the word compression. I use shrink just because it keeps that S for our acronym. Helps students remember variables. And then we'll look at horizontal, stretch or shrink. And what's important there is we're going to look at whether or not we have something that looks like, just like with our horizontal and vertical shifts, it depended if we had f of x plus some constant or if we had it inside the function. What was going to matter here is if we have a constant times our function or we have a constant times our variable. And so let me go ahead and go to the next slide. Vertical stretch. And like I said, our form here is if we go from f of x to a some constant times f of x. But now it's going to matter if our a is bigger than or equal to 1, or if when we have our f of x and a f of x, if a is between 0 and 1. So here, a is a fraction, right? So it's less than 1. It's some partial amount. And so we'll look at both of those examples in turn. So here consider f of x equals the square root of x. I'm going to fit my table in over here. I'm going to go ahead and start my graph here. We have x and f of x. So we know we can't go any smaller than 0, 1, 4, and what's 3 squared? 9. So the square root of 0 is 0, 1, 2, and 3. And I'm not going to go all the way over there, but if I graph that, 0, 0, 1, 1, 1, 2, 3, 4, 2, 4, 5, 6, 7, 8, 9, 1, 2, 3. I need to be pointing it that way. And it looks something like that. So that's my f of x. But now, consider some g of x that's 4 times the square root of x. So that means our g of x is going to be 4 whatever this value is. So 4 times 0 is still 0, but now we have 4, 8, and 12. And so if I graph that, I have 0, 0, 1, 1, 2, 3, 4. 2, or at 4, we're at 1, 2, 3, 4, 5, 6, 7, 8. And over at 9, instead of at 3, we're at 6, 9, 12. So we're aiming up that way, and it looks like that's our g of x. And just like when we did our vertical shift, we could look at this as being 2, and because our a is a 4, 2 times 4 is 8, right? So that distance from the axis to the point gets stretched that far. It gets stretched all the way up to 8. And now that's different than, say, for example, if we had h of x equals 1/2 square root of x. Because now, I'm just going to put my h of x column. Half of 0 is 0. Half of 1 is a half. Half of 2 is 1. Half of 3 is 1.5, and so on. And so if I were to graph that, we would have something. I'm going to use orange for my graph. 0, 0, at 1, 1/2, at 2, 1, at 9, 1 1/2. That's our h of x. And so there, we could call that a shrink, because that distance of 2 was shrunk down to 1. And so if a is bigger than 1, that's a stretch. If a is between 0 and 1, that's a shrink. And so depending on if that number we're multiplying by is larger than 1, the distance from the x-axis will increase. And if it's between 0 and 1, it will decrease. And now notice I didn't say, well, what happens if it's 0? Or not 0. What happens if it's negative? Because if it's 0, the function becomes 0. But if it's negative, then we just have a combination of a reflection about the x-axis and a stretch. And so after I introduce the horizontal stretch and shrink, we're going to get to multiple transformations and putting them together. So, next slide. Here we have horizontal stretch or shrink. And so now what we will have, and I'll just go ahead and divide it down the middle to begin, we're going to have f times a, or f of a times x, or f of a times x, right? Before the a was out front, but now it's on the inside. And here, when it's greater than 1, or between 0 and 1, if f of x equals, the r square root's getting a lot of work, so let's go ahead and use the absolute value of x. G of x equals the absolute value of 2x. And then we'll go ahead and say f of x is still the absolute value of x, but g of x over here, nope, I can't call that g of x, we already called g of x. Call that h of x is the absolute value of 1/2 x. So we can go ahead and make our table. X, f of x, g of x, and h of x. And then I will graph it over here. We'll go, I don't know, what do I go? -4, -3, -2, -1, 0, 1, 2, 3, 4. The absolute value. G of x now is twice the x value. So 2 times -4 is -8. 2 times -3 is -6. 2 times -2 is 4. 2 times -1 is 2. 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 6 and 8. So if I graph my original f of x function, it looks something like this. And if I graph my g of x, we're at 0, 0, and then 1's at 2, 3's at, or 2's at struggle and a half, 2's at 4, 3 is at 6, 4, I knew something looked off there. That point was in the wrong place. So now, 2, 4, 3 goes to 6, 4 goes to 8, and the same thing happens on the other side. And that is our g of x. So if our blue was our f of x, and g of x is steeper, you can think of stretching that up vertically, but rather, we won't think of it as moving up down, but rather each of these points shifts in, right? And so that's what we see happening here. And if we work on our h of x, where we take our absolute value of our half x, so -4's half is -2, so we're at 2. -3's half is -1.5, so we're at 1.5. -2's half is at -1, we're at 1. -1's half is -0.5, so we're at 0.5, 0, and then 0.5, 1, 1.5, 2. Pick a new color, so we're at 0, 0, 1, 1/2, 2, 1, 3, 1.5, 4, 2. Then we copy those onto the other side. We can think of stretching that out that away. Because in this first case where we have a horizontal shrink, what happened at x before now happens twice as fast, right? So before, at 2 we were at 2, but now we're there twice as soon. We were there at 1, or yeah, that's exactly what I'd say. Or where we were at if we'd kept going down to say 6, to get 6, it happens twice as fast at 3. 4 happens at 2, 2 happens at 1, right? Things are happening sooner. So we can think of shrinking that vertically because our points get pulled towards the y-axis. And then if it's between 0 and 1, we call that a stretch, because now things take twice as long to get there. Because before we were at 2 at -2, But let me pick a different color because now it's getting hard to see. Before we were at 2 at -2. Now we don't get there till 4. Or at 1, we were at 1, but now we only get to a half, and so we end up stretching out. Do I care if you can say, if we have f of a times x, and a is larger than 1, we have a horizontal shrink, or between 0, a, and 1, it's a horizontal stretch. No, I care much less about whether you can name them what they are, but I do want you to be able to graph them either through using a table at first, or eventually moving on to being able to transform your library of functions. And so now, let's work on some examples. Multiple transformations. And so I'm going to give you 1, 2, 3, 4, 5, 6 examples just right here. That way if you want to pause and try these on your own. They are x minus 2 cubed plus 1, negative x plus 1 cubed plus 2, negative square root of 2x, 1 over x plus 2, absolute value of x minus 1 minus 2, and negative square root of x minus 2 minus 3. And that minus 3 is outside, and so if you're handwriting, a trick I always use is I put this little drop on the end of my square root, so I remember that negative 3 is on the outside. And remember, our sequence is help students remember variables. 1, 2, 3, 4. We do a horizontal shift. We have stretch or shrink, a reflect, and we have a vertical shift. And so for each, it's important that we identify our library function. And so here, x cubed is our library function. Our second one, x cubed, is still our library function. Square root of x, 1 over x, absolute value of x, and square root of x. And that just helps us remember, well, what does the graph even look like? It's our x cubed, our square root, our 1 over x, our absolute value, right? And so that's what we're going to start with. And then we need to think about our horizontal shifts. Let me pick a different color. We have a horizontal shift, another horizontal shift, a horizontal shift, a horizontal shift, a horizontal shift, picking a different color. A stretch and shrink, remember that's when we have something on our, where does that number appear if we have a stretch or a shrink? Well, it's either going to be in front of our function or in front of our x value. So we have one here, and that's the only one we have. Then we have our reflections. So we have a negative here. So we have a reflection, reflection, a reflection. And then do we have any V's? Any vertical shifts? We have a V, we have a V, a V, and a V. And so that's a lot for this slide, so let me move on to the next slide. I'm going to rewrite that first one, where we have x minus 2 cubed plus 1. And we said it has a horizontal shift and a vertical shift. And so I would say, good practice is to draw your original. So 0, 1 cubed is 1, 2 cubed is 2, 4, 6, 8, negative 1, 2, 4, 6, 8. This is our x cubed graph. And so what we need to do is we have a horizontal shift of 2 units right, because when x is 2, this piece is 0. So first, we have our h shift. So that's 2 units right. So if this is our origin, 2, up 1, and then all the way up to 8, down 1, and all the way down to 8. And that's our result from the horizontal shift. And then I'm going to go ahead and write my V, H, and V. Vertical shift plus 1, so every unit gets moved 1 up. And we get something that looks like that. So we took this original graph, x cubed, we moved it 2 to the right, 1, 2, and up 1. So it looks something like that. Good. Let's try another one where we combine them together. I'll do the next one. We have our negative x plus 1 cubed plus 2. And remember, our order is H, S, R, V. And we said this one has an H, an R, and a V. And so our x cubed looks something like that. Our horizontal shift now is 1 unit left. So now we have something that looks like that. We have a negative, and so this one, a negative on the outside, a negative in front of our function, means we're going to reflect it about the x-axis. So now we have something, instead of being there, left 1, we reflect it about the x-axis, and it looks like that. And then, so that was our H, our R, and then our V. We need to shift it up units, so 2 units up. So here, left 1, up 2, still opens up that way, opens up that way. And of course, you can still draw your table, you can calculate each of your points, and in fact, I'm going to encourage you to do so. But for the sake of time, I'm not going to calculate all of the points, and I'm going to apply our transformations directly. So another one, 1 over x plus 2. This one only has a horizontal shift. So if we look at it this way, our 1 over x looks something like this. It has an asymptote at x. Let me pick a different color. It has an asymptote here at x equals 0, and 1, or at y equals 0 and at x equals 0. And what we're going to do is we're going to shift it 2 units to the left, because at negative 2 is where we get our 1 over 0. And that means I draw my coordinate grid. And we'll go ahead and translate our asymptotes, because that's helpful to help me draw it. And it might be worthwhile to calculate what it is at 0. 1 over 0 plus 2 is a half. And so if we look, my line is actually a little bit high. I thought it looked it at a half. Something closer to that. And so this is our 1 over x up top, and this is our horizontal shift result, 1 over x plus 2. Let's look at one or two more examples. Absolute value of x minus 1 minus 2. HSRV helps students remember variables. Has a horizontal shift, no stretch, no reflect, and a vertical shift. And so we're going to go, is it left or right? So we're going to go right 1 unit. Started writing the word unit weirdly, and then I was like, that's not what I want. And then we have 2 units down. And so we have our coordinate grid, our absolute value looks like that, absolute value of x. And so we go right 1, down 2. So from here we go right 1, down 2. And we can put in some points. Here we have absolute value of x minus 1 minus 2. That's our H and V combination. And I'll do one more before we conclude. Negative square root x minus 2 minus 3. HSRV. Has a horizontal, no stretch, a reflect, and a vertical. And so we apply them in that order. So for memory, our square root looks like that. And so if we do our horizontal, we're going 2 units to the right. So this is at 2, 0. Looks like that. Horizontal shift, then a reflect, and it's the negative out front. So it's about the x-axis. So that step is H, R. We're still at 2, 0, but now we're reflected. And then our vertical shift is down 3. 1, 2, 3. And it looks like that. So what we're going to focus on really in this section and moving forward is thinking about how can we use our library functions, our go-to basic functions, to graph these transformations of other functions. I'll see you in the next video, everyone.